Hello and welcome back to this series of videos where we together learn how to use Lean to create proofs and have them checked by Lean. So let's look at a really simple task. So we are given a formula y equals x plus 4, and we are also given another fact that x is 3. So we have two facts: y is x plus 4, that establishes a relationship between x and y, and we are given another fact that x is 3, and our task is to prove that y is 7. Now again, you might say it's really easy. Just as last time, the task was really easy and probably not worth writing lots and lots of content to prove it. But what we want to do is to develop our thinking so that we can think in a structured way about mathematical proofs and translate that into Lean code. So that's what we'll try and do today. As I said last time, it's actually more difficult with easy tasks because they're so easy, our brain just jumps to the conclusion. Just for completeness, we're going to say that they are all real numbers. And that's an interesting point actually. This habit of being complete in our description of the problem is something that Lean will help us do, because it sometimes can catch when we've been incomplete or wrong about some of those assumptions, and then the conclusion doesn't follow. We'll actually see that in a later video. So let's have a think about what that proof written in plain English, breaking it down into steps, might look like. So that habit again of writing down the given facts. We're given a fact, y is x plus 4. It's a given fact, called it 1. X is 3 is another given fact. We've labelled it 2. And now we think, well, what are we trying to do? We're trying to prove something about y. Do you remember? So we have to prove y is 7. So we have to prove something about y. So our conclusion will have a left-hand side of y. So it makes sense to start with y. What do we know about y? Well, we look back at the facts and we see, well, y is x plus 4. So we can use that. So y is x plus 4. And we still have to justify that line. We have to justify every line in our Lean code. So we justify this by fact 1. You might say, duh, we've just been talking about it for the last 10 minutes. But we're writing this down because this is how we write Lean proofs. So getting into that habit and thinking in this way is important. So y is x plus 4 using fact 1. So we can't argue with that now. Now we're saying we want to get rid of the x because that's not helpful. So we look back at the facts and say, is there anything that can help with that? Well, yeah, the second fact tells us that x is 3. So whenever we see an x, we can replace it with 3 because they're the same. We're given that as a fact. So we've got x here, we can replace it with a 3. So we're doing a substitution using fact 2. So x plus 4 becomes 3 plus 4. The x has become 3 using that fact. So now we have y equals 3 plus 4. Our conclusion, we wanted that to be 7. How do we justify that? Again, don't fall off your chair. We do have to think about justifying every step. So how do we get from 3 plus 4 to 7? Well, it is arithmetic. And as we kind of spent a long time last time talking about the piano axioms and going all the way back to the basics, we won't do that because it's not, we don't do that in everyday proofs. But we do need to say, that this is an arithmetic operation on these numbers, and they weren't natural numbers; these were real numbers, and that's still valid. 3 plus 4, 3 is real, 4 is real, then 7 is the answer, which is real. So that's y is 7. Is now the conclusion, which is great. That's what we wanted to prove. Let's just look again at the justifications. So this was using fact 1, that one, and this is using fact 2, and they're all kind of substitutions in a way, because y is substituted with x is 4 plus 4, and then 3 is substituted with, so x is substituted with 3 there, and we'll use that in our Lean code. So that's the overall structure. So again, if you want to download these slides and have a look at them yourselves, I've written down just what we've just said. We start with the facts. We want to prove something about y. The first fact tells us what y is. We then have y is x plus 4. That's great, but we want to get rid of the x and with something that we can simplify eventually towards 7. And the second factor is helpful because x is 3, so we say y is 3 plus 4. And finally we do an arithmetic evaluation, and that justifies why that's 7. As I say, it can seem disproportionate, the level of detail or thinking about the structured approach that we're doing, but it's important because we're training our minds to write lean proofs which require that kind of structure and that kind of justifying every line. So let's look at some lean code, and today we will talk a lot more about what the code does. But before we dive in, you'll see the familiar kind of elements. You'll see that x and y are established as real real quantities. So whatever x is, it's a real number. We have two hypotheses, two given facts now. We have y is x plus 4 and x equals 3. Those are the two things that we have to work with. And here they're labelled H1 and H2, hypothesis 1, hypothesis 2. You can name them anything you want. It's sensible to name them things that are intuitive. And then we've got the overall statement that we want to prove, the overall objective, y is 7. And remember, this thing, colon equals, is a way of signalling that whatever's on the left is going to be proved on the right. So whatever came before is going to be proved by what came after. It's like a justification. And so all this is the proof of this theorem here. This was the name that anonymizes the theorem, so we couldn't give it a proper name, but we can just say example because we're not going to use it again later. So calc is a strategy we're going to use for this proof, and it's essentially calculating the result, which is what we've done. We've calculated that it's 7. So it's sort of saying a quantity equals something, and that equals something, and that equals something, and that equals something, until we get to what we want, and that's the calculation strategy. So we've set out we've written down the thing we want to prove something about, which is y. We've said it's x plus 4. Why is that? Because we're given y is x plus 4 as a hypothesis. So the justification is by rewriting. So RW is rewriting. It's one of the tactics using H1. So we're rewriting y as x plus 4. And we're allowed to do that because we're using hypothesis 1, which matches y and says, yep, if you see y, and then you can use x plus 4 whenever you see y. So that's why y is x plus 4, because you say y is y and y is x plus 4 using this hypothesis. The next line, we make some progress. So this underscore means we could write x plus 4 equals, but we just, that would get quite tiresome. So as you've seen in maths proofs, we often leave out the left hand side. It's just assumed that it's this thing here. Let me draw a picture. So in maths at school, you might have seen, x equals something, b plus c equals d plus f equals d plus g over h, and so on, equals 7. So we didn't write x here, and we didn't write b plus c here, d plus f. It's just assumed. So instead of having anything here, when we write maths solutions for our school exercises, we often leave the left hand side blank, but in lean we use the underscore to mean it's this last thing. So if I say a equals b, underscore equals c, underscore equals d plus f, underscore equals 7, then what we've got is this thing is that b equals c, this thing is c equals d plus f, and this thing is d plus f. So that's what it is. It takes on that expression. So it's just shorthand. You might have like myself, I initially thought it meant A, so this A equals A equals A equals. Although often it's equivalent, it's not the case. It's actually the previous right-hand side is the next left-hand side. Great, so we've got x plus 4 here equals 3 plus 4. We got rid of the x and replaced it with a 3. How do we do that? How do we justify that? Remember that symbol? We justify it by the rewrite tactic again, but this time using hypothesis 2, which tells us that x is 3. So that x is rewriting x plus 4 as x plus 3. In fact, it's rewriting x as 3. So that's how that's justified. And then we simplify, we do the arithmetic, we evaluate 3 plus 4 to be 7, and that's using the num-norm tactic again. So we've seen the num-norm tactic able to justify why 4 is more than 1. If you did the exercise, you've justified why 10 is more than 4. And this time we've seen it just do simple addition. 3 plus 4 is 7. So there's quite a lot in norm num. In fact, there's quite a lot more in norm num, but we'll see some of that. Let me draw a picture just to summarize that. So norm num is a tactic, and inside that tactic other people have written lots and lots of code that encodes quite a lot of mathematical knowledge that we can reuse and that we can use to justify as we move from one line of proof to the next. We've just scratched the surface on that. We've seen that we can justify 4 is more than 1 by norm num, by this thing. We've seen, so it knows about more than. If you did the exercise, we know it can do 10 is, we've seen 4 is less than 10. I think that was what we did. I can't remember exactly, but it was the less than symbol. So it knows the less than operator by norm num. So you can do that. And in today's video, we've seen that it can do 3 plus 4 equals 7 by norm num. So we can use it to justify that as well. So it's got lots of, by its name num, it's got lots of concepts and knowledge encoded into it about numbers, greater than, less than, adding, equals. So that is the proof, and if you look at the slides or the blog, you'll kind of be able to read in slower time some of the things we've just said. What we didn't cover is the top line, which looks like a comment, and it is. So if we start a line with dash dash, then Lean will ignore it, and it's useful for us to write comments, and that's a good habit to remind ourselves what that code does or explain to others what the code does. Some people will write lots more. If you're doing professional work, you would be writing a lot more, about the code, but even just a one-liner is a good habit to get into. And this is the thing that imports the math library and the tactic part of that math library so we can use those tactics. So importing means extending the core language of Lean with all the work that other people have done and packaged up as a library. It's the same in other languages. Python has lots of libraries, and there's lots of C libraries and so on. So it's a common way of packaging up useful work to be reused and shared as a library. What else did we want to say about this code? So we've talked about the comments, we've talked about the import, so it loads in information. We've talked about the theorem name, and we've talked about why it's example. We did that in the previous video actually. We've talked about establishing what the types of those variables are, the real numbers. The hypotheses we've talked about. We've talked about establishing the goal, and then the symbol colon equals, which means that we're about to go into the proof now. So this is just that first line, this line here, which is essentially a statement of the theorem that we want to prove, and then there's the body of the proof. So here's just a picture kind of summarizing that. I think over time we'll develop this because there's more to be said about what that first thing is. But for now, we can think of it as a name. An example is kind of like an anonymous name. The types, hypotheses, and then the objective. And then that thing says, right, we're about to justify everything on the left with some proof. So we talked about calc, and that's a strategy. We won't talk about it a lot today, or in the coming videos actually, because to really understand it, you have to see different strategies for doing proofs. But lots of the beginner ones that we'll be looking at just use calc. So the best thing to say about it is, well, I'll draw a picture. So a calc approach is to say something equals something equals something equals something equals something equals something, and that's the thing we want to prove. And we get there by a series of kind of steps for calculations and justifications, and that's the calc strategy. So you can see it's very common. Most proofs that we come across are of this form, particularly kind of beginner level maths. So we'll ignore that for now. We'll just assume that all the proofs we're going to do are following this strategy until we get advanced enough to look at something different. So that's probably enough to be said about that now. We can just make it invisible to our eyes for now. And then the core of the proof we talked about, y is x plus 4, we justified it by rewriting. That was using that tactic. Same for the next line. And then using arithmetic. Now, that's great. How do we know that the proof is correct? Is there any feedback? We didn't really talk about that last time. So the thing that gives us feedback is given a name, Infoview. You might think, wow, why does it deserve a name? The reason it deserves a name, so unlike lots of languages where you run them and if there's an error, the console or the command line will tell you there's an error. The way Lean works is that it's kind of interactive and it's always running what you're typing, which means for most of the time it's telling you that your code is not complete and correct, because as you type it, it hasn't been completed. But if you think it's complete, the Infoview will kind of tell you if there are any problems. The reason it's given a fancy name is because it can do a lot more, which we'll come to in the coming videos. If you've got a more complicated proof, or even a simple one, it will tell you what it's doing at each line. So it gives you an insight and information view into how it's kind of resolving and confirming that your proof is correct. So it does a lot more, but we won't touch on that for a while. We'll gradually learn more about it. But we'll demo that today actually. So it's usually on the right, whatever that means. So if you're using the Visual Studio Code thing, it's a panel on the right. If you're using the website, it's a panel on the right. But the important thing for now is to say it's updated as we edit our code, and it provides warnings and errors. So let's actually look at this code running for real in Visual Studio Code. And as I said, all the code is online on GitHub, so you can download it and explore it yourself and have a play. So this is Visual Studio Code with the Lean extension installed, and this is a Lean file, so it recognizes it as Lean. If you're using the website, you just copy and paste this into the website and you'll see the Infoview. So this thing on the right is Infoview, Lean Infoview. And we know this proof is correct is because it's saying there are no messages, 0 messages, no messages. No messages is good. Like they say, no news is good news. No news, no messages means there's no problems to report. It's working fine. If I was typing this and I hadn't quite finished typing, so I've just deleted the end of that line, you can see there's loads and loads of things that it's telling us. We won't go into what they all mean. You'll learn over time what some of it means. I've got to say, it's not always that intuitive, but it's a new language and a new library, so it's still improving how it reports errors. And that's kind of some of the things that the developers are working on are to fix that or improve that. But for our purposes, for now, we can say, oh my god, there's lots of messages, something's wrong, even without reading them. we can sort of say, right, there might be something wrong here that we have to look at. For us, there wasn't anything particularly wrong. It's just that I didn't finish writing. So if I finish off writing the proof, they've all gone away. Let's see if that was actually useful, what it said. So what did it say? It said, unexpected end of input. So the line hasn't been finished. Expected a bracket or an indented tactic sequence. So yeah, expected a tactic, because by means we're about to justify this by something, by a tactic. In fact, if I hover over by, this editor will kind of tell us a little bit about what that thing does, what the instruction or the code does. So it's looking at the documentation, so it's sort of saying by tac constructs a term with an unexpected type running. Okay, so it's not that useful for us at this level, but if you're more advanced, you'll be able to understand that. So yeah, let's finish that off by norm, num, and it's helpful because it's trying to suggest how we might complete that. In fact, if I hover over it, does it? Yeah, so it's looking at the documentation, telling us what this tactic does, and you can read about that. In fact, the rewrite tactic, let's rewrite it. Let's look at the documentation for that. So rewrite is like rewrite, but also tries to go. Okay, so these are kind of for more advanced readers. That's why we're doing this course, because a lot of the content out there is for advanced readers. But for our explanation, it allows us to rewrite these expressions using the given facts. Great. Is there anything else we can say about Infoview? So let's have a look at some of the richness of the Infoview. So if I click at the beginning of the proof before we've got into it, so I've clicked after the word calc, we can before it even, it tells us where lean is, not where we are, where lean is up to that point in the code. So if we're at the beginning of the proof body, we can see what it thinks the state of play is. So it knows that x and y are real. It knows there are two given facts, two hypotheses, h1 and h2, and what they are. And this symbol means the current objective, the thing that's needing to be proved. And to be proved is y is 7, which is correct. That's the objective. So that's where it's got to at that point. As we progress in the proof, that will evolve, but we'll talk about that in a later video. So that's kind of just a first look at what the Infoview is. If I'm just to test it again, if I use the wrong, if I say h1 instead of h2, it can't rewrite x plus 4 as x plus 3 using the wrong hypothesis. So I've deliberately introduced an error here, and you can see it says tactic rewrite failed. I didn't find the instance of the pattern. So the pattern is y is x plus 4. Sorry. So y is x plus 4. It can't turn that into 3 plus 4 using hypothesis 1. It's telling us that that rewrite tactic failed. So that's a useful error for a change. That's great. So that's telling us there's an error, a problem. It's telling us it's at line 8. So line 8 and position 24 along. Usually just the line number is fine. In fact, Visual Studio Code will put a red kind of line underneath where it thinks the problem is. So let's change that back to H2, and suddenly all the error messages have gone. Fantastic. Notice if I click at the end after the proof, there's no more goals to be proven. So that's why it says no goals. So over here, the goal is y is 7. Over here, there's no more goals because it's done. So just another little bit about the Infoview. That's actually a lot more than I wanted to talk about Infoview, but I guess got flowing. So yep, we talked about Infoview. We said that there's no messages means there's no warnings or errors, which is good. So if our proof is correct, it's because if there's no warnings or errors, then it doesn't think there's a problem with the proof. We introduced a deliberate error, and we could see that there was a warning printed out in the Infoview. As I had said, Lean is new, MathLib is relatively new, it's under active development, so sometimes the error messages are not always that helpful, and there is an effort to kind of make them more helpful. But this one was actually quite useful. It's saying tactic rewrite failed, and that was enough to point us to what the problem was. Fantastic. So we've looked at a bit of real code today and talked about it in a lot more detail. So pretty much everything here should make sense. If not, just rewind the video and listen again. And as I said last time, we'll present at the end of each video a really simple exercise. And the idea is not to spend our time trying to solve some difficult mathematics. We'll keep the maths easy, just to give us a chance to use Lean, because that's the focus. So that's why they're called easy exercises. So, and they're all following on from what we've just done. So today, the exercise is to prove that y is 0 given two facts. Y is x squared minus 9 and x is minus 3. And for completeness, we've said they're all real numbers. Now, let me just illustrate why I call these easy exercises and why they're a practice for Lean rather than doing maths. If we look at our code, you can see, we've got a thing to prove. We've got two hypotheses, and all the steps are done by rewriting. So this exercise can be done just by that. You can just take that code and edit it, and you should be able to arrive at the proof that y is 0. Now, just because this is early in the course, I won't solve this for you, but I'll just draw a picture just to help if you're having trouble with that. So we said we would follow a structured approach. So we write down the given facts. So facts, and they are, well, what were they? We said y equals x squared minus 9. What was the other fact? X is minus 3. X equals minus 3. So that's fact 1 and fact 2. And then in the main body of the proof, we want to prove something about y. Actually, we didn't say what we want to prove. To prove. We want to prove that y equals 0. So in the main body of the proof, we start, it's usually a good strategy, to start with the thing, writing down the thing we want to prove something about. So y equals, well, what does it equal? Well, we're given, we can't say y is 0 because that's what we have to prove. That's cheating. We've given a fact about y. We're told that it's x squared minus 9. So x squared minus 9 using fact 1 by 1. And that's great, we made progress. But we want to get rid of the x because that's looking at our target, our objective, y is 0. And that's just a pure number. So somehow we've got to get rid of things that aren't numbers here. 9's a number, so we can probably do some calculation. But x is not a number, so we could try and resolve that in some sense. So let's look at the facts again to see if they're helpful. Yep, the second one tells us that x is minus 3. So that means x can be replaced by minus 3 squared minus 9. So you can see it's the same expression, but with x replaced by 3. And we justify that by using fact 2, that one there. So that one was that one, and that one is that one. And then we can do a numeric calculation. So minus 3 squared is 9, minus 9 is 0. So we say by arithmetic. So I've written a plain English proof here, and that you can see here this is the same structure as the Lean code. So we write the facts, we've got to prove, and this stuff pretty much translates almost directly into Lean. So that should be an even easier exercise. So any problems, do kind of reply and comment in the YouTube comments, and we'll have a conversation. So I hope you enjoyed that, and look forward to even more interesting videos where we look at more and more capabilities of Lean and the kinds of more interesting proofs we can do, but we'll take it slow and gentle. See you next time. Bye.